Yeah. All right, so I guess we should go ahead and get started. We're very happy to have Junwu Huang here today from Perimeter Institute. Junwu got his PhD at Stanford under Savas, and then moved to PI for a postdoc, and that's where he is currently. Not as a postdoc, and he's going to tell us today about some cool.
You never know.
Never know. New string production mechanisms and gravitational waves. So please, Junwu, without further ado.
Yeah. It's always very nice to come to NYU and visit. I learned a lot of things from people here, and as I was reminded last week, this is almost the only thing that I'm doing which doesn't involve anyone who was at NYU or like who is currently at NYU. So this will be what you are going to hear. So over the last few years, we've been interested in understanding string production in systems which has large observation numbers and energy density. So I was invited to talk about this paper for October last year. Cannot make it because of visa reasons. So the good thing is in the meantime, we did something new, and I'm also going to share with you this new developments. Okay. So now it's not working. Okay. All right. So the talk will be the following. So first, I will give you a very short review of light bosons, especially those ones that are very weakly interacting. Then I will show you a video of the simulation of events we call the string bosenova. We'll be telling you about how this string actually form in the superradiance cloud around spinning black holes in a gauge U1 series when there are self-interactions. And then I'll also show you some new results where we see also string formation in global U1 series. In the end, I will be telling you about some phenomenology, mostly in the gravitational wave. Okay, so I think this crowd doesn't really need much introduction about light bosons, so this is I think all of you have seen this. All the energy scale that we can potentially access, with the smallest being Hubble scale today, and the biggest being the Planck. So the model is somewhere in the middle. And by light boson, I mean anything that is heavier than Hubble today, below which it will be massless. All the way to not really just EV, but somewhere it could be all the way even to 10 to 12 GeV. The definition of the light boson depends on the environment you are in. If you are talking about inflation or reheating dynamics, then even a particle that heavy could be behaving like a light boson. And for the second part of the talk will be it could be even a particle that is very, very heavy. So there are so this is the more conventional range, which is motivated experimentally from as a dark matter candidate. They are produced in the early universe potentially purely gravitationally through the misalignment for scalars or pseudoscalars, and through inflation and perturbation for example the dark. Okay, so there are theoretical motivation for these particles. For example, the QCD axion is motivated as a solution to the strong CP problem. There are additional motivation from the perspective of string theory. Of course, so here is also something. So on the experimental side, the realization that led to a lot of progress is thinking of these light bosons instead of individual particles that collide with your detector, but as waves. So in particular, people are thinking of them as weakly interacting classical waves, which pretty much works for all laboratory systems that we are considering. So, and the intuition is if I have a finite density as the particle gets lighter, their competent Bohr wavelength increases, and the interparticle spacing gets smaller. And at some point, they will overlap with each other. At this point, you should use the wave picture. So in this talk, we are going to challenge this paradigm. We are trying to ask the question, is this always going to be a very weakly interacting classical wave? Okay, and the observation is that if you go to early universe, especially when like these particles are produced, then we are talking about really large occupation numbers. So just to use the dark photon example, if we are talking about particles like micro EV or 10⁻⁵ EV, then if you just compute the number density times the computed wavelength of the particle cubed, this number at the time, like as early as it can be accessible with the CMB measurements, this number is 10 to the 29. When we think like it was produced during inflation, for example, like this number is 10 to the 54. And if we are talking about superradiance cloud, famously, like this number is 10 to the 76. So these are huge numbers. And the question is, are there new dynamics which can emerge when the occupation number is so large? So we're going to show you that in certain cases, this picture of weakly interacting classical wave breaks down, and then there are new dynamics and new phenomena we can emerge. So following Neil Weiner's advice, where I first gave a talk here, like in 2019, where I want to show some results, I should show an animation first. So here, this is actually not an animation; it's an actual simulation, which we run of spinning black hole surrounded by a vector superradiance cloud. So here we go. So the cloud is developing like around the spinning black hole, and the amplitude is growing. So at some point, the amplitude is large enough such that there's a classical instability which emerged, which produced this green line, which is a string. So the string will grow in size and eventually like get back onto the black hole, disappear. By which time the cloud almost totally disappeared. Okay, so so in the first part of the talk, I will be telling you like what happened in this movie, what are we simulating, what is the process led to the growth of the cloud, what is this object that emerged, how did it emerge, what led it to get bigger, and what are the experimental signatures. All right, so this is what I said, and we're going to talk about the bosenova. So what are we simulating in this case is a dark photon, and a dark photon from a abelian Higgs model. So this is basically the action. You have a Huang gauge symmetry, under which you have like a scalar which is charged under it, and the scalar has a magnetic potential, so that at like at low energies, phi is equal to V. And both the Higgs and the dark photon gets a mass as a result. So we are interested in what is known as the Stuckelberg limit, which is when the Higgs is much heavier than the dark photon. This can be realized naturally by just taking the quartic coupling to be much bigger than the gauge coupling. Okay? So in this limit of lambda over g squared going to infinity, the Higgs is very heavy and the dark photon is very light. So as a part of a physicist, I would integrate out this heavy Higgs and be left with a Lagrangian that only contains the dark photon, right? So it has a kinetic term, it has a mass term, and then like has some interaction, which all go as at least like a g to the 4. So people have played with this action here, and which tells you at some point there are instabilities which can exist where like these terms become large. But what I will show you is like it actually happens much before that. Okay, so we're going to show like this is not quite this whole story. You will see it. Okay, but before that, let me also tell you about black hole superradiance. So this is an effect which grows this cloud around the spinning black hole, and it happens wherever you satisfy this so-called superradiance condition. When the rotation angular velocity of the black hole is bigger than the mass of the dark hole. So for this talk, we'll be using like h bar equal to c equal to 1 units. Well, also feel free to ask questions anytime. So wherever like this condition is satisfied, then these light bosons can extract energy and angular momentum from the black hole and the populated cloud. This cloud is described by gravitational fine structure constant, which is basically gm of the black hole times the mass of the particle. And superradiance process will be efficient if this number is in some range between 10⁻³ to as big as about 0.5. Okay. This is well going. And just to give you some numbers, let's say like we take alpha like which is 0.1, then like for sort of like a 10 solar mass black hole, a stellar mass black hole, this will be happening for a particle mass of 10⁻⁴, 10⁻11. And if we are talking about supermassive black holes, which probably do something to at positive timing array, then these particles can be as light as 10⁻20 eV. So over this 10 order magnitude range in mass, there are some black hole in the universe which is populating this cloud. Okay. All right. So so then the next question, like what is this green thing which popped out, right? So this is as we like we will explain this from the perspective of this condensed matter literature because it is first observed by first noticed the solution by Abrikosov in 1957 when he was looking at type 2 superconductors. So what he like noticed there are solutions which contain like a profile localized solutions which contains a profile where featuring at I equal to 0 like a symmetry restoration, localized symmetry restoration. So the vortices has a structure like this. It has an inner core where the Higgs field goes from phi equal to v to phi equal to 0, and over a length scale of 1 over m phi, and on a much bigger length scale of order like 1 over mass of the dark photon or the photon, that the magnetic field has a profile which grows logarithmically towards the center. So,
question, are the longitudinal modes the only ones that are relevant, or transverse modes as well?
For the photon?
Yeah.
So for now, like it's only the longitudinal mode. Like later, like we'll see like how does the transverse photon actually interact with this object. Yeah. So so this is the topological defect. And so in terms of rho, like you see it as a line where like a phi is equal to 0 out of a region where phi is equal to b. But like the topological nature comes from this non-trivial winding of the phase of A, right, of the phi field. And you see like the angle of phi goes from, I'm not tall enough, and this is not very stable, but like, so it goes from 0 to minus pi over 2 to minus pi to pi over 2. So like there's a winding, there's an opposite winding, so there's a vortex and a vortex. Okay, so so this is about the scalar field, and there's also quantized nature for the gauge field. If you take the a mu integrate along this circle around the vortex, you will find that the total magnetic flux, which is threading through this vortex, to be phi naught, which is equal to 2 pi over g. So in superconductors, this is actually pi over g or pi over e because the Cooper pair has charged. So, but like this is basically the object. It has a unimagnetic flux. So the flux is going inverse as the gauge coupling, and then like it has a non-trivial wire. Okay. So next question: how did it get produced? Right. So so to show you this, I'm showing you handmade animation this time, where we are going to see like a string popping at I equal to 0. Okay. So, but to start, we have a uniform magnetic field. Okay. And as a result, uniform phi amplitude, which satisfies this condition. Okay. So so if you look at this part, you will notice that there's a critical field. Okay? So which is basically where the square root equal to 0, and you can rearrange these parameters and get BC2, or the second critical field of superconductor, which goes at lambda v squared over g. Okay? So at this critical field, basically all supersymmetry, not all like superconductivity is lost, and you have total symmetry restoration everywhere. Okay. But what Galecko noticed in 1966 is that there is actually a lower threshold where something dramatic happens. So and here like I'm going to like I say that let's say like I have a small perturbation of magnetic field at r equal to 0, which goes upward. Okay, if we were to satisfy this equation, then like the phi amplitude will have a dent in this region because p is bigger. So have a dent. This magnetic field wants to be like because of Meissner effect, magnetic field wants to be in regions where the symmetry is restored, or like a simpler, like it just wants to be in regions where the dark, this photon or the dark photon is lighter. So the magnetic field wants to cluster a little bit more in the central region. So it does that, and phi would continue to go down, satisfy this equation. And this is a wrong way direction for above some magnetic field strengths, and you pop a string at the r equal to 0. Okay. So of course, this doesn't happen at 0 magnetic field because you still need to overcome radiant energy of this phi field as the phi profile develops. But in this instability, or at any time, all you need to overcome is basically just this gradient energy. So so this localized instability can happen at a much lower magnetic field strength compared to the global restoration. And Galacco was the first one to compute this, which is equal to the quarter coupling work half times v squared. He calls it the superheating field strength because the phase transition that led to formation of these vortices is a superheated phase transition. Importantly, like in the limits where lambda is much bigger than g, this is much smaller than BC2. Right? So the superheated phase transition, which produces these vortices, happens much earlier than the total restoration ratio of the symmetry at a much higher field strength. Okay, so this critical field that Galacco found doesn't happen in any superconductor. Okay, and the reason is because conventional or like all superconductors you can build has an edge. So it is much easier for the flux contact to creeping through the edge and at a field strength which is much smaller than that. But for our case, when we are simulating this vortex formation in the dark photon superradiance cloud, there's no edge, and hence like we see exactly this field strength at which like the vortex form.
What's the two coupling constant strengths? Like you said, G was 2 for the superconductors.
G is 2 times the electric charge.
Yeah, right. But then what about the other coupling?
The other coupling is depend on the superconductor. It's a complicated. Yeah, it's a material dependent thing. It can be anything. So for type 1 superconductor, lambda is smaller than g squared. For type 2, it's bigger than g squared.
I understand the runaway direction is causing the localization of the X and the magnetic field profile.
Yeah.
What's causing the phase of the scalar to wander around this localized energy density?
So like so certainly like you won't be able to produce like a in some sense like a one string, like because that like you always produce either a line or a pair. So I should yeah. Right, so it's instability which also has like the phase winding like at those sort of collisions, but it will always go in pairs. Right. Okay, so so let me show you this video again. This is basically what we talked about. The cloud grows, the string form. Then in the next few slides, I will show you why does it grow and what happens afterwards. Okay. So so why does it grow? So to show you why does it grow, I'm going to run through this animation, basically putting like all these things together. So first, let's start with a vortex in isolation. This vortex is pointing inside the spring with a magnetic flux that is, let's say, either pointing out or in. Around this vortex, the A vector has this profile. Okay, so say the hat over GR, and you can do the line to go around, and you are going to find 2 pi over G flux. So now I'm taking this vortex, I'm putting it to be moving in the, let's say, x direction. when I have like a magnetic field flux, which is moving in the x direction, it generates electric field. And you can compute the electric field by just taking the time derivative. And so you can do some manipulation, and then like the orange is what you get. Okay, so this is the electric field which is produced around the string. You can look at it, and you notice it's a dipole field. It is indeed a dipole field, and the dipole moment per unit length, because it's 2D, is a dimensionless quantity which is equal to the velocity of the string over the gauge coupling. And this electric dipole moment is pointing down. So now I'm putting it in an electric field background, okay, or dark electric field background. So the electric dipole wants to align with the electric field you put in, and it wants to get bigger such that the dipole energy of d dot e or minus d dot e gets smaller, more and more negative, right? So the way to get that is for this object to accelerate. So v will increase. So it'll be accelerating in the x direction. So what you have is if I have a vortex, I put it in a background electric field, it will be accelerating in the x direction. Okay. So this is basically what happens in this picture from here to here. There's residue cloud electromagnetic field. This electromagnetic field is interacting with the string, pushing it around, and giving it the cloud energy to the string, making it go bigger. So afterwards, in the simulation, the string just collapsed back onto the black hole. And the reason for that is because in this particular simulation, we cannot really go to what is known as the supercluster limit. We cannot take lambda over g squared very large in a simulation which involves this spinning black hole and the cloud globe. Okay, so it's a numeric like a computationally too intense. So even for real. So what we cannot see a lot of strings forming in this environment. The maximum we achieve by making this thing bigger and bigger is 3. Okay? But in reality, when we actually taking this quantity to be very large, you should expect many strings to form like in this environment. So, but from like all the things I told you, we understood that the formation of this string doesn't really care like if there's a cold black hole in the middle. So, and artificially putting a field which is growing. Okay, and so this is what we did in an empty box. Now I can simulate lambda over g squared much bigger. And as you see, like this gauge field is field energy is growing. So the dotted line, it's the field strength or the energy density inside the field until like it hits some critical value when the strings form, and the string will again take over the energy density while the gauge field, the background gauge field will have energy which decreases over time. But this simulation allows us to see additional features because now we can produce many strings at the same time, and we can let it evolve afterwards, after the gauge field are all like think about. So what you see is what the condensed matter people call a melting phase transition, where these long strings, which has some like a long range order, it's hard to see from this picture, goes totally crazy to this next picture after some time evolution. Now, like the system has all kinds of small strings everywhere, and any long range order is totally lost. So this there is a cascade of energy density into smaller less fields in the system. Okay, so why would we care about this? Well, instead of like this one loop which has a 0 center of mass momentum and it always collapses back onto the black hole, when you form a lot of loops and they all form with some like a random velocity, these loops will be flying out, right? And they will be some of them will be flying out, half of them will be collapse back onto the black hole, and some of them might be attached to the black hole in some specific way, such that you can swing some noodles like algorithms. I think we would propose. So, so in this case, these strings which come out will oscillate, emitting scalar radiation, emitting vector radiation, and then like also gravitational radiation. And this gravitational wave are some signal we can look for for example, in metal. So I won't go into much details, explain this signature, but just show you some qualitatives. So the first thing is we have this melting phase transition, which produce like strings, which are very much smaller compared to the size of a black hole, which means we can have gravitational wave signals even at much higher frequency compared to 1/GM. So I personally am not very excited about these detectors, but it does produce a signal that you can see in these detectors if the string bosenova is actually happening. So the other thing is the signal will start at very high frequencies when the melting phase transition complete, and then like slowly go to lower frequencies as this cloud grows. So it will have a reverse chirp type phenomena where like it start here, and depending on the spectral index of the string length distribution, it will move to smaller and smaller frequency following some of these lines. Okay. So for this particular parameter set, I think you don't need to do any real analysis to know that this is excluded, because it's really like it feels like a bear at the detector. Okay, so but like for you can if like the black hole is a little bit further, or like the parameter is not chosen to maximize the signal, then like it might produce something that we can extract from another. Okay. So this is about the string boson. Okay, so so summary of this part, I told you about this new phenomenon we discovered, which is called string bosenova, whereas the vector cloud grows to some critical value from the string, and how they might lead to detectable signals. Such an effect can also potentially happen in the early universe if you want to produce some dark photon dark matter. So this is a picture I took from Jack Weiner. What we see is that even if all you require is that you do not have vortex formation in dark photon dark matter at the time of CMB, you exclude basically all of this shaded region that people are looking at. Okay.
Sorry, what's the size of the box in the melting phase transition simulation?
The size of the box is like a.
Sorry,
I
I
forgot.
forgot. It's localized around the black hole, right? It's not like the whole Hubble.
It's you can have like a universe size, like so like the size of the box is a little bit bigger than 1/MA, a few times 1/MA.
Oh,
yeah.
It depends.
So but like in cosmological simulation, it doesn't really matter. Like I just have some energy density which grows, and I know like where the instability happens. And once the instability happens, I form some string. The energy density of the cloud is of the cloud of the dark matter is totally gone. Yeah. So if you want it to not happen, you need to live below this line. And for the conventional production mechanisms that we have from inflation, for it to not happen even during inflationary time, you need to live below this line. So any production mechanism we know is excluded from this mechanism. So we don't know how to produce that. Document is the conclusion of this one. All right, so that's half of the talk. So in the next half, I will be telling you about this new phenomena we found. It has some like analogy to the Niagara Falls. If you fall off a cliff, like you are going to go turbulent. But you are going to see like why there is this analogy. But if you are asleep, like now it's the time to wake up.
Sorry,
to see some
I would like to wake up. So tell me this massive vector,
yeah.
right? If you have massive vector field, and if you postulate that it is the entire dark matter,
yeah,
then you say it could not have been produced at any stage.
Or the
Like
production...
what exactly this exclusion plot? How should I read it? Should I conclude once and for all that dark matter is not a massive vector?
Okay, so let me be careful here. So if you are above this line, then it doesn't really matter like how you produce it. We are just saying like if this particle is going to be dark matter, have the right energy density to be dark matter at the time of the CMB, it would have produced the vortices.
And it would
So
probably
anything
be
above
bad.
this is true.
Sorry, and it would probably be bad to produce
Yeah.
vortices.
So when you produce vortices, all of the energy, most of the energy will go into this vortex. So it's no longer dark matter. So as a result, all of this range is excluded. For the inflationary line, it's a particular production method. It might be produced in a different way at a later stage. Then it will like be this line will move. This line will move depending on the production mechanism. Okay, but like this would be like above this line will be a hard exclusion. In between this depends on how you actually produce it.
When?
Where and how you produce it. Yeah. Okay.
All right.
Okay, back to the phenomenon we'll be talking about is called the periodic stream burst. And again, following Neil's advice, I will show you a video. Okay, so what you are going to see in this box is just strings. Okay, and you will have to wait a bit because now at this point, it's a lot of complicated things is going on in the box, but no string has produced. Okay, so the field of perturbation is growing until now around this time you're going to see something great.
Who is growing?
Some field
Scalar
is growing on the background, but like now, yep. Okay, so the blue line should top up. Okay, so now it's a little bit longer. So these blue lines are strings. Okay, in the 3D box. So they form, they disappear.
So they disappear, they're moving out of the box and just.
No, they just annihilate. They annihilate. Now I'm giving you like to read it, but like okay, so they go again and they disappear again.
What's the time scale?
Huh?
What's the time scale versus seconds? The cosmological.
It depends on like when does it happen. I will give you more details about this. Cool. But like for this, just to what we are seeing is strings periodically formation, annihilation, and if you are interested in gravitational wave, there will be periodic gravitational wave burst. So so in the next part, I will be telling you about like this global Huang case where we see some periodic string. So this is work with Michael Frederick, who is at Perimeter, and then Neil Simonson, who is now a postdoc at Princeton. Yeah. But he's a gravity person. All right, so so what we are simulating is very simple. It's like a basically like this action here. It's an action with a U1 global symmetry with a mechanism again like a one model like potential. So so this is basically the potential. In this theory, I have a conserved current, which is basically the U1 current. So the field can be phi can be separated into the radial mode rho. Okay, so the rho direction, and then like the theta direction, which is winding around. Okay.
Supposedly this is dark matter or what? Phi.
We are not going to specify what it is. It's people use this mechanism, for example, in these papers to produce axions, like it's related to axion dark matter production. This is some repeating dynamics people were studying. Okay, so like this type of potential dynamics was used in various like system from reheating, axion, or baryogenesis. Okay, so there are many places where this could happen, and even for the Higgs boson.
But sorry, you start with some initial phi and you let it expand or what?
Okay,
You
so
put it into
yeah,
expanding universe. What exactly are you doing?
I'm going
okay.
into this. Okay, so this is the potential. Okay, so and the initial condition is just I'm taking this field to be frozen at some like a large-ish phi over v, and we are going to define like what is large-ish in a bit, and I can either push it in the circular direction, give us an initial uniform angular charge density, or like I can just release the exactly at rest and let it oscillate. So first, I will be telling you what happens if I just put it here and then let it oscillate back and forth.
No expanding universe, just a 2-pi periodic box.
It could be like a Boson-Minkowski background, like a periodic box, or you can have like expanding universe. I'm first going to tell you about the Minkowski case, and then I will be telling you what happens in expanding universe. Okay, the simulation that you saw before is a 3D box with with no expansion. Okay, so but the initial condition is just like I'm here. Okay, and I let it go. Okay, so here, let me first show you not a cosmic evolution, it's a periodic box, as you already said. And I'm, especially like in this case, I'm showing a 2D simulation. Okay, so the x and y of this plot is just like the 2 dimensions, spatial dimensions. And in these 3 panels, you are seeing the radial mode amplitude, basically like the rho amplitude, the theta dot, okay, the rotation speed in the circle, and the theta value at a different location. Okay, so the initial condition is here, so which is where phi is equal to 5 times v, I think, for the simulation, and then like theta is equal to 0 to start with. So initially, this phi is going to just go oscillate back and forth. So you are going to see it mostly being like a dark red, and for a short amount of period like a lighter red. And then like this guy is going to just go from 0 to pi, 0 to pi, right? So so with this, let me play this video. Okay. So this thing is going back and forth. This thing is going 0 pi, 0 pi, and then something starts to emerge in the middle. Okay. Let me stop it here. Oops. I didn't want to go further. By the way, maybe it's too late, but like if you have like a problem with seeing things flash, like there are some videos which are not good. So like if you are looking at here, like what happens is you develop regions which are rotating in one direction. Okay, so rotating clockwise, and then there is an equal amount of region which is rotating counterclockwise in this video, in the middle. Okay, so then the system continues to evolve. At this point, like the color, like in the center, is no longer changing anymore. At this point, you basically have like almost circular motion of this field, like in this potential. Okay, in the deeper regions of the pink, also in the gray. And the theta angles start to have like a differences between these regions, and on the boundary, you start to have. Oh, sorry.
Is there some initial perturbation about what breaks the symmetry?
You put in like a 10 to minus 5, like a density perturbation. That's all you need. Okay, so so at this point, like this winding like around these locations is almost all 2 pi, and vortices start to form on the boundary. And these vortices will form, they will annihilate on the boundary, and you are going to see more details later. But since there's a stop, now you can look at, for example, this region. There's clear vortex.
I thought you didn't have a boundary.
Huh?
I thought you did not have a boundary. Aren't you doing it on a torrent? You said periodic boundary condition.
Yeah, it's like this line is identified with. What do you mean by boundary? No, I mean like the
I'm
boundary.
asking you, what do you mean by boundary if you're on a
Boundary,
torrent?
I mean like the regions which interpolate from the pink to the green.
Okay, not the boundary of the
No,
box.
not the boundary of the
Okay.
box. Sorry. Yeah. So like we call these regions domain boundaries, where interesting things happen. Thanks for the question.
You need some transverse initial condition, like some initial motion around the circle.
No.
Right? So what happens if you just let it go without any sort of transverse cake?
It's the same thing happens.
No, they said there was 10 to minus 5 perturbation.
Yeah.
It was perturbed slightly.
There's some small like density. Basically, the rho amplitude is perturbed like from place to place by a 10 to minus 5 difference. Yeah, but like the angle, like you can have a charge, not a charge, doesn't matter. And with a charge case, it's even more weird. But we are going to go to that. Okay, so what we see. Okay, so I have a nonlinear potential, right? So what initially happened, which led to this growth of perturbation, is basically parametric resonance, and this has been studied like in our papers, starting from I think even Bremberger and co, where so you see there are different K modes, and K here is normalized to the mass of the radial mode. So K tilde, K over mu. And for different like a rho over V, rho over V equal to 1 is the minimum. There are different K modes which are growing like some perturbation. Okay, the y-axis is the rate of the fields. So the interesting thing is that the growth of the perturbation is in some particular direction. So like here, like I'm basically looking at the Y model from above. There's the X and Y direction of the phi, or the real and complex direction. And I have like a field which is oscillating back and forth like this. This is the zero mode. The perturbation is going to grow like in the phi Y direction. And it is going to grow with a phase offset for a variety of K modes that is pi over 2 in amplitude. So when you add like this zero mode oscillation and this perturbation, which is a pi over 2 offset, it's like adding two linear polarized photon, like with a phase offset, you get circular polarization. So that's why like the field start to rotate one way or the other, and since like there are non-zero K modes, then like half of the region is rotating one way and half the region is rotating the opposite direction. Ooh. We didn't lose electricity. Okay, so you can see it here better. So this is a counter, basically showing the counter rotating regions. So so there's a region which is rotating very fast in one way, and then like there are a couple of regions which are rotating very fast in the opposite direction. On the boundary of this region, though, there's a gradient which needs to grow, right? Like the theta go one way, theta going the opposite way. There's a gradient. So on the domain boundaries, there are large gradients.
Sorry, I cannot contain myself. Why should we care about nonlinear dynamics of this particular model? I mean, so sure, if you have nonlinear thing, there will be evolution, there will be cascading of energy to smaller scales. Why should I care?
So so you are going to see like there are gravitational wave signals which are like
so you will turn it into dark matter or what?
It will like I think like it first like for the dark matter part, I think like again like the dark matter production mechanism people were talking about doesn't work. Okay, so there are some mechanisms people talk about.
So where would this field be produced so as to produce gravitational waves? During inflation, you are...
So like during reheating, for example.
So you are basically saying Kaufman and Linde are okay, but now I put on top of it gravitational waves. I just need to understand.
No, like Kaufman and Linde like is not seen like these. Well, like, let me go go through. Like I will show you like the phenomenology.
If you promise that there is a usage, I can.
Yes, I will go to the point and then like there is some usage and then there is some like anti-usage, but like yeah. So but like on these boundaries, you have like this gradient which is growing. Okay, so so like if we zoom in to these domain boundary regions. So, so in this plot, it will just be like this yellow line, and these arrows are showing like the direction of the gradient. In here, like you are going to see strings popping and disappearing, and then like they are going to all form on these mountains. So, so you will see some domain boundary forming, and then like there are some string appearing on this wall, like it disappear, appear, disappear, and this happens periodically in this much smaller zoom in region of the box. Okay. So if I look at the picture, okay, to stare at a particular like a domain boundary. So what happens is first like I have like all of this arrow pointing in the same direction, where like the gradient is large. As when it reaches some critical value, on this domain boundary you form like a vortices. Okay, so you see like this vortices of rotation of the arrow. You see vortex forming here, vortex forming here, and then like after these vortices, after they form, they get pushed apart by the Magnus force. So they get pushed apart. So similarly, you can see in this plot, but these two figures already show you all the details. Okay, so what is the formation condition? First I will be telling you about like a microphysical like a formation condition, what happens along this wall. So this is basically the field profile, like along one of these domain boundaries. You have the two counter-rotating regions separated by this domain boundary, where there are large or like a large-ish like a gradient theta. So this picture is very actually analogous to a situation which was studied by Feynman like 70 years ago, when he was looking at a superfluid which is flowing through a thin orifice. So you have a tube and the superfluid is flowing through, and you have like this blockade, so that it's only a small hole that the superfluid can flow through. So if you zoom into this region, this is the profile of the velocity field, which resembles this. And he famously derived this critical velocity of the superfluid flow, which is basically this quantity, where m star here is the mass of the helium, basically. So if you turn this velocity field back to the gradient theta, it says gradient theta has to be 1 over a, where a is the size of the orifice. So we basically exactly say this see a critical gradient theta, and which matches basically like what is predicted in this condensed matter literature. Okay, so we can also identify global conditions. So so here, like I'm showing you the basically like the critical rho amplitude to start with to form a vortex as a function of the initial charge density you put in. Let's first like forget about the right hand side. Just look at the small like a J naught limit. So this is basically like the situation where I'm releasing this field as rest. Okay, so what we saw it, and like in all of the literature we found, people were saying like this critical field is like a square root 2 times b, which is basically saying like you need to be as high as in the potential, such that like this the potential energy density is exactly the same as V naught. Okay, but if you when we run this simulation, we were surprised to find that you don't actually need to be here. You can be like even much smaller, 1.2 times V, and at which point like this potential energy at this point when this is set to 0 is only 2.29 of V naught. So what this is telling you is like you can be like oscillating back and forth, like a small amplitude here. You never experience like anywhere close to here, and then like this dynamics of counter-rotating region formation, stream formation we already have. Okay, so for example, like in the old Andre paper, he claims that like you need this up here, but actually it's not. And this is another like example, like it's similar to the gauge case, gauge field, gauge U1 case, where again, like I don't have like enough energy density to restore the symmetry everywhere, but locally I can form strings where the symmetry is restored. Okay, so it just tells you like this even like a very mildly nonlinear systems, you can have instabilities which leads to stream formation. So the strings of the form, they are actually confined to some 2D boundaries, so in 3D, and or like 1D boundaries, these domain boundaries, and they never move into the region where theta dot is non-zero. Okay, so we see that both in 2D and in 3D simulation, and it was kind of surprising. So happening. I'm not sure what's happening. Sorry about that. So there are a couple ways to understand it, but here, like I will just be telling you about this story based on particle vortex duality. So under the particle vortex duality, which is a good duality in 2 + 1 dimensions, a U1 a series with a U1 global symmetry is due to a series with a U1 gauge symmetry. The vortex in the U1 global symmetry series is mapped. Vortex in the this global U1 is mapped onto charged particles in U1 gauge series. The velocity field or the gradient field we were talking about before is mapped to electromagnetic field in this way, and like the dynamics will go through. So so let's just take this picture. of like vortex formation and mapped onto the gauge case. So here the vortex is going to be charged particles. The gradient of theta is mapped onto electric field, which is pointing in the perpendicular direction. So basically, this vortex formation is basically showing a pair production, and this theta dot is mapped onto magnetic field. Okay, so these are regions where magnetic field is positive and negative. So what you're seeing, that's the vortex, forbidding this vortex to go into these regions is basically the Lorentz force. In this dual picture, like even if they go very fast, once they enter, they will get a pushback. Okay. So this pushback is important because we see that the strings actually form and annihilate periodically, right? So normally when you have like strings, for example, in 3 dimensions, the most likely they are not going to hit each other head on. They are going to cross each other at an angle.
But if you wait long enough, wouldn't all energy go to high wave numbers? I mean, this periodicity cannot be forever. After all, there must be constant cascading to small scales.
So I can, just let me show you this figure, okay? So like here we see this periodicity and the string number as a function of time. So as you see, like basically like the archesis that with a constant separation, and the separation we can predict. So we ran the simulation actually for a very long time, as long as we could. And this periodicity continues to exist because the energy density that is lost into radiation from like this string constant production and annihilation on the domain wall or domain boundary is a very efficient way to actually like release energy into the scalar radiation. And in this case, we see a total of like 137 period, and the amplitude only decreased by a little bit.
So some oscillon, whatever.
Huh?
It's like an oscillon. Ultimately, it will die. You do not doubt it, right?
Eventually, like this energy will go away, but like it will happen for a very, very long time. So let me just skip this. And we have tested this also in expanding universe. Okay, so this is again like a 2D simulation where I put in like a universe expansion, and I have normalized such that all the dominant energy density stays a constant. So here we see like the number of string per co-moving box is a constant over time, and the period follow this simple formula that is basically this. We see like in both two spatial dimensions and 3 spatial dimensions, I satisfy this exact equality, where A1 is the scale factor of the first stream formation. These are like basically constant related to the first stream formation. I is the ith stream formation, and AI is its scale factor. So in 2D, like you see like this grows because this is 5 to 5, 6. But like in 3D, like this is equal to 1, so delta A is actually a constant. Okay, in the expanding universe, this will be periodic in delta with a constant delta A, and so each of like this stream formation and annihilation is going to produce gravitational wave. They will all have like their characteristic of frequency, like set by the model parameters, and the relation between the subsequent bursts is basically set by this time where the burst happens. And if you turn this A relation into a frequency relation, what this tells you is I have a mechanism to produce strings annihilation into gravitational wave with constant frequency shift between like a burst to burst. So if I'm going to see this gravitational wave, then I'm going to see a frequency cone of this gravitational wave spectrum with equal delta F between all of them. So this is the signal that we are. Yeah. Okay. All right. So in the last slide, 3 minutes, I will show you something that surprised us a little bit. So here, this one like it really gives you trouble, like if have problems with flashing. So so here, like what I'm doing is I'm taking like this maximum have potential, and I'm putting the field to be rotating in almost a circular orbit. Okay, so so this is why, and the theta dot is very large to start with, which is why like it's all green like in this pattern. Okay, and then like on the right, I'm showing you the dt theta dot subtracting the mean. Okay, so so now let's play this video. So the first thing what happens is that again you form this differential rotating regions. Some regions is rotating a little bit faster, some regions is rotating a little bit slow. Okay, and you form this differential rotation. But at this point, you start to see some crazy things happening in this video. So for some reason that we don't totally understand, but we like it's probably some nonlinearities. Inside the differential rotation region, there are pop regions which are rotating in the opposite direction of the initial direction you notice the field in. Okay, so all of the field is going to be in circular motion almost, with some fraction of the volume to be in the opposite direction. Of course, charges conserve. That's why like the green and the red have different like a total area. Okay, so this string formation dynamics also happen like in expanding universe, and it persists all the way to when like this field is doing very slow movement, like at the bottom of this potential. Okay, at which point string of course cannot exist anymore; they all go away, and the volume of counter rotation also decreases to 0. But for a very long period, until like you really get to there's not enough energy density less than 0.3 V, V top, like the string number to grow all the way to the end. So like the string number, average string number will grow towards the very end. Okay, so so we like this circular motion in particle physics model building. People talk about things like conation. There are models which produce axion called axion kinetic misalignment, where you seems to suggest, where people suggest like, oh, like if I have some electrical motion, these things will circularize and be nice like dark matter production mechanism. We like baryogenesis mechanism after like dying. All of these involve like stability of some circular motion in our one-model potential. This result seems to show that these things are not very stable. This is the best we can put in a circular motion, and still like the stability develops such that you always have like regions which are rotating like in the opposite direction, and the energy density in the strings is always like order 1 of the energy density throughout. Okay, so like do these things even happen? I don't know, but but that's something to figure out. And here's the conclusion slide. I told you about these things called string bosenova and what type of signatures we can look for them. And then this in a very simple one-model potential, you can produce strings that periodically produce and annihilate. That gives you some unique frequency spectrum of gravitation. And these are the things that we're interested in searching for. And maybe we can find them. That's it.
Questions?
Yeah.
No, for the global string case, I naively would expect like the gravitational wave signal is very suppressed since you dump energy back into just the axions. But you're saying
Even like the fraction of G mu, right? Like the G mu fraction of the string energy will go into like G times V squared, the string tension, will go into gravitational wave, and that is enough to be observed.
Sorry, I had exactly the same question. Can you explain more carefully? So suppose you make it your scenario for reheating following Linde and Kaufman.
Yeah.
Okay. Now you are saying what those people overlooked is those periodic bursts of string production, correct?
Yes.
So are you saying, I didn't quite understand your answer. Are you saying that the amplitude can be detectable?
The frequency, like the amplitude of the gravitational wave you produce can be detected. Yes.
Really?
Yes. And you will Like at low frequencies, you might be able to see this periodicity as a comb of frequencies, yes.
But I thought that depends on this theta dot over Hubble ratio, right?
Say the dot over Hubble ratio, yes.
That was, so, I mean, theta dot could be very small, for example.
Like
Like, sorry, I think it was Hubble over theta dot.
Hubble over
Sorry,
theta dot.
Yeah.
So theta dot could be very large. In that case, like you are going to have like peaks which are wide, and then like they like touch each other with which are separated by a small amount. So then like it will be hard to like see individual ones, but you will see like the amplitude will have some oscillation, like almost a constant backbone. If like the h over theta dot is not that big, then like you might even be able to see like individual period. So that's what we are trying to figure out. So in this simulation, we do not have like a what's it called, like a program built in to like extract the quadrupole moment as a function of time to compute the gravitational wave spectrum as a function of time. So we are working on the like that like a module to actually see like what is the actual spectrum of the gravitational wave that will be coming out of this burst first.
And who will see them?
Huh?
Which detector will detect?
Oh, like
them?
so if it is some reheating, like then it will be like very low frequencies, something like a PTA.
Oh, so
Yeah.
there are constraints already? I mean,
Yeah,
I
there are
want to
constraints
understand,
already.
are you taking it seriously
Yeah.
or just an entertainment with?
No, like I take it seriously. So the other thing that we want to understand is whether this happens for the kicks, the snell model kicks. So then like these forests will be happening at LISA. You're going to see like these forests of peaks in LISA gravitational wave spectrum. If you see that, then you know like the kicks, snell model kicks has a displaced amplitude to start with, and then like it goes through like some periods of this string formation. Yeah. But we are looking into that, and putting SU2 like on this like a simulation is quite hard. So I like so there is like some uncertainty. I don't know like whether it will actually happen like in the exactly the same way, but we'll find out. Yeah.
These detectors actually have the frequency resolution to see a comb like this. Is that, I mean, I know they have like.
Right now, like they don't. Yeah, like a PTA right now certainly don't. LISA would.
So you'd stack a bunch of events, and so you'd resolve.
No, like it's some like a early universe like a gravitational wave, which gives you like this frequency comb structure. So now like if you take like the signal at the different frequencies and you do a Fourier transform, you are going to see this period. Right, like so basically like you are going to see. So most likely you are not going to see like so the extreme is you see something like this, right? But like most likely you are not going to see something like this. You are going to see something like this. Okay. So then like what you are going to see is like this periodicity of oscillation. And it will be like a constant like a delta F. So so you can use a data analysis tool to extract that.
So wouldn't it be easier to do this in the time domain? Because you just get a spike, right? If it's a flat Fourier transform, you just get a delta
What do
function.
you mean? That's
The Fourier transform of a constant, right, is a delta function. So it's roughly constant.
Yeah. So I'm not sure like I totally understand what you're saying. Like I have an A of omega, and I just do a Fourier transform of A of omega. Yes. Yes.
Now, what happens with the standard misalignment stories? Let's say you already have some axion condensate without any kinetic or kinetic misalignment.
Yeah.
So that condensate would persist through this epoch of string formation, or it would get destroyed?
You mean like the Kibble type of production?
Yeah,
or like
just for actions, just a
like
standard misalignment.
Yes, standard misalignment, like those things will just oscillate back and forth. Yeah.
But you'd preserve the condensate that you, let's say, generate during.
Or if I start with some theta which are different at different locations, I don't know how much they preserve. Yeah, I'm not sure. We didn't put that in. Yeah. Like every simulation we have, like the theta is a constant as always, because we do not want like a Kibble to contaminate. We want to make sure like these are the strings we form, not like forming through the Kibble mechanism. But in principle, you can put that in and then like see how they interact. We haven't done.
I guess I had things like pre-inflationary in mind, but we can
Yeah,
talk later.
pre-inflation ones, yes. We don't know whether it destroys those.
Sorry, standard pre-inflationary, you're not displaced on the wine bottle, right? You're somewhere on the circle, but you're
Oh,
not.
you don't know that? It depends on Hubble
Right,
speed,
right.
and the radio mode. That's the whole, like, that's the
Right,
point of
right.
Keisuke, right? Like, you can be like, oh, very far. But, yes, like, if you're very far, like, this is what happens. It's not like some circular.
Sorry, I just meant that for misalignment to work, you don't necessarily need it to be.
Yeah, don't need, you don't. Yeah. But you can also not like really forbid very easily, like media space.
Kind of relates to maybe these background condensate questions, especially like say with the Higgs. Like oftentimes when these like strings form, there's friction with the background plasma, and
Yeah.
that like stops, it prevents it from moving for quite a while until the density of background particles drops sufficiently.
Mhm.
Like, I mean, are these background particles, especially with the electric phase transition, something that will prevent this from
Oh,
actually?
yeah. So like,
happening?
we don't know what happens, like if you have a plasma. Like for the standard Higgs, yeah.
Right.
Yeah, good point, because it is reheating after all. That's when you produce all the particles against which you will experience the friction, right? Maybe it's just successful reheating and not much strings oscillating for a long time, right?
Yeah.
Yeah, good point.
Like for the standard Higgs.
But he's saying, because
Yeah.
like one of your applications was primordial gravitational waves produced by reheating.
Yeah.
But reheating is there in order to reheat, meaning producing standard model particles and stuff like that. And friction against those particles perhaps will stop your strings and just make them part of the thermal background.
Yes, potentially, or like it can potentially even make it bigger, in fact.
Yeah, I don't know.
Like because like you have like a circular motion, and then like if you have friction, like the circular motion will be damped. Then like it will like want to be elliptical, like all of these trajectories in the field space, and then like more of this instability will grow. Things gets more complicated. We don't know like once you put a thermal mass in, which is strong, a couple is strong enough, then we don't know what happens.
Okay, maybe we should ask questions after thinking Jen one more time. Open panic.
Yeah, okay. Oh, you want me to put it back?
Oh, it's okay, actually, I. Let me just stop recording.
Yeah.
Should we give that some live?
Sure. I think it's about